Good afternoon everybody. I'm Paul Grant, I'm from Glensound Electronics and I'm Chief Engineer there. And today we're going to talk about HD Voice, which is the new system for mobile phones. So in this presentation we'll look at what is HD Voice. We'll take a brief look at the history of telephony and why we're limited to 3.5 kilohertz. We'll look at the evolution of codecs, how we've got to where we are today and why HD Voice was developed. We'll look at how HD Voice compares with previous codecs. We'll look at how it works in practice, how you can use it as a broadcaster, the availability, which networks it will work on, solutions for broadcasting, and we'll have a brief listen to a sample of HD Voice as used in a real broadcast environment, and then a summary and questions. So first of all, what is HD Voice? Well, HD Voice is actually the commercial name for the G.722.2 AMR wideband codec. Obviously rather a mouthful and not very consumer friendly. So the telecoms companies wanted a unified name which described AMR or wideband in terminology familiar to consumers. HD is commonly accepted as the symbol for high quality and therefore was the obvious choice for them to use. So it was developed to overcome the limitations of standard telephony, which as we all know gives you 300 Hertz to 3.5 kilohertz roughly. And it's been that way really for the last 50 years. So HD Voice extends the coverage at the low end down to 50 Hertz, giving you a much more natural sound, and at the high end up to 7 kilohertz. The frequency response is broadly similar, of course, to G722 that we're probably all familiar with. So, as I said, a brief history. The reason we're stuck with 3.5 kilohertz audio is that early analog telephone systems used frequency division multiplex to squeeze a lot of voice channels into trunk circuits. The frequency of separation used in the carriers was 4 kilohertz, and therefore this restricted the audio bandwidth because of filtering to about 3.5 kilohertz. Digital telephony was later developed but had to interwork with the old analog technology. 8 kilohertz as a sampling rate, of course, gives us roughly 3.5 kilohertz of audio bandwidth, so matches in with the older systems nicely. It's also a multiple of 4 kilohertz, so it reduced interference with the frequency division multiplex systems. So historically, that's why those sample rates were chosen. When the mobile phone networks emerged, it made a lot of sense, especially given the limitations of the technology at the time, to use exactly the same sample frequencies and of course the same audio bandwidths. So, codecs used within the mobile phone networks, we won't talk about the very early systems, but starting with GSM, the data channels that you had available to you were either full rate of 13 kilobits per second or half rate of 6.5 kilobits per second. The lower rate was introduced to enable mobile phone companies to reduce congestion. When you had a lot of traffic, it meant you could squeeze in another set of phone calls and of course gain revenue from it. So the early GSM codecs were appropriately named full rate and half rate and used a form of coding called linear predictive coding. In 1997, this was changed to an enhanced full rate codec. This incorporated the previous codecs and added a codec with better quality. With the introduction of 3G UMTS, the AMR codec was introduced. You see it here as AMR narrowband. This is a consequence of AMR wideband coming along and the need to distinguish between that and the older system. So AMR narrowband stands for Adaptive Multi-Rate Narrowband. It used an ACALP or algebraic code-excited linear predictive algorithm. Again, as before, it worked with an 8 kHz sample frequency, giving you 3.5 kHz of audio bandwidth. This again has to squeeze into the existing GSM channels, so it runs at bit rates from 4.75 to 12.2 kilobits per second. It's worth mentioning at this point that the algorithms chosen for mobile phones were designed very much with the fact that the radio interface was not necessarily going to be completely reliable. So there are a lot of techniques built in that enables the air interface to protect the most important parts of the data within the codecs. This is an essential difference between using a radio system and something like ISDN, which we're all familiar with as a fairly robust data medium. I think the telecom companies are perhaps a little embarrassed that in the last 50 years there's been no real improvement in the quality of phone calls, certainly in terms of frequency response. And I think both the manufacturers and the telecoms providers felt that there was a need to do something about this in an age where we have high definition television. So they introduced this new codec called AMR-WB, which stands for Adaptive Multi-Rate Wideband, the technical name of which is G.722.2. Worth pointing out that although it's G.722, which we're all familiar with, the codecs bear very little resemblance to the G722 that's used in ISDN. They are much more sophisticated algorithms with much lower bit rates. It uses a speech coder very similar to the ACALP processors used in AMR narrowband, but with some differences. The main difference with AMR wideband is that it uses a fixed sample frequency of 16 kilohertz. This enables us to get a 7 kilohertz audio bandwidth. And at the same time, they extended the low frequency end down to 50 hertz. 300 hertz, of course, always makes audio sound rather thin, despite the fact that it's got a limited upper band. 50 hertz makes it sound much more like natural voice. Again, bit rates run from 6.6 kilobits to 23.85 kilobits per second. The higher bit rates are not used within the mobile phone network. The AMR wideband codec is intended for use in other systems as well as mobile phones. It can be used for storage and use in other data transports. There are 3 different configurations that can be used within the mobile phone network. At the moment, they only use configuration A, which is actually known as the anchor rate. This rate is chosen because it will fit into the 13 kilobits per second familiar to GSM, which would allow interworking with GSM networks, although GSM is an old technology and it is unlikely that they will go to the trouble of upgrading. Now, at 12.65 kilobits per second, the rate that's used as standard in mobile phone networks, you get a quality equal to or better than G722 running at 56 kilobits per second. Now, we're all familiar with it running at 64K in ISDN networks. If anybody's ever listened to 56K working, say, with America, you'll find that there's not a great deal of difference. It's a very tiny difference. The network can reduce the bit rate, which will, of course, reduce the quality, although you will still get the same 7 kilohertz audio bandwidth, and it will do this only in a temporary mode to cope with poor radio conditions. So if you were to move into a slightly dodgy radio area, it will fall back but should recover. And there is indeed one even lower rate, but again, you can expect this to be temporary. However, even the intermediate lower rate still gives you a G722 equivalent of 48 kilobits per second. So I'm sure you'll agree it will probably be not much degraded over a G722 circuit.